Good morning, everybody, and welcome to my talk about functional programming in Kotlin, where we try to explore the arrow library. First, a little bit about myself. My name is Ties van der Ven. I'm from the Netherlands, working for a company called J-Driven, and I'm quite proud to call myself a software engineer. And that is because I'm quite passionate about the engineering part of software engineering. And with that, I mean, I like the high-level concepts, the high-level abstractions, and just the general problem-solving aspect of software engineering. And because I'm quite passionate about this subject, I love to talk about it. So you may think I came flying all the way from the Netherlands here so you can learn a bit about functional programming. In practice, I just get to talk about my favorite subject for about 15 minutes, and it's kind of rude to interrupt. On that note, my friends and family would like to thank you for finally getting a break from all this. But I wasn't always an engineer. In the beginning of my career, I worked on this big monolithic application. And when I say big monolithic application, think millions of lines of code. And with millions of lines of code comes a lot of complexity. And with a lot of complexity comes a lot of bugs. So most of my time at this company I actually spent fixing and introducing new bugs. And if you fix bugs for long enough, a few things start to happen. First of all, you start seeing certain patterns between them, as in, hey, this is basically the same bug, but in a different context. And you also start to get a bit of a hate against those, and basically start a lifelong quest in trying to prevent these bugs from occurring in the first place. And in this quest, basically, I slowly discovered functional programming. And it's important to know here, I didn't come to functional programming from an academic point of view. Most people view functional programming as a very academic thing for mathematicians as such. I just came to it from a practical point of view. I had problems and I needed solutions. So if there's anything I would like you to take away from this talk, is that functional programming is not just for mathematicians. If you just have a bit of a desire to learn why things actually work and want to prevent problems from ever happening, look slowly into functional programming. So what are we going to talk about today? We're going to do a little bit of functional programming theory. We're going to talk about the M word, monads. We're going to see how monads can affect a real-world application. And we're going to finish up talking a bit about some optics and about smart types. So let's start with the functional programming theory. And with that comes the question, what actually is functional programming? And this is quite a difficult question to answer, since I think every programmer will have a slightly different answer to this question. So I'm just going to give you my answer. And my answer is, I think functional programming is a story about love. It's about loving your compiler. Because within functional programming, we try to take as many runtime exceptions and turn them into compile time exceptions. So basically, we want to create a situation where if you're not doing things correctly, your code will just not compile, instead of getting a runtime error in production. Basically, the ultimate shift left in that sense. It's about loving your team members by writing explicit code. It may be very obvious, but we kind of just want our code to do what it says it does. That's basically all it is. And I'll show a bit of an example of that later on. It's about loving your cake. Very important, and we'll get to that later as well. And about loving your functions, because of course it's functional programming. So let's talk about functions, and most specifically, function signatures. So here we have a function foo, which takes a string and produces an int. So the function signature of this is given a string, produce an integer. And if you abstract it even more, given an a, produce a b. And now you may think, yeah, that's basically every function ever. And that's true until we encounter errors. So when we encounter an error, our function is now in an invalid state, and we either need to short circuit, so stop executing until we can either recover it or, well, the thread crashes. And Kotlin has, well, two major ways, recently three major ways to actually handle these exceptions. First is the runtime exceptions, the nullability system, and the result type. As you notice, the result type has a little asterisk on it. That means I'm not really going into it, but I'll mention it a bit later. So exceptions. We have a divide function here. As you all know, if you divide by 0, bad things happen. So we cannot allow that. So in this case, we're trying to solve that with throwing a runtime exception. So we check B to see if it's 0. And if so, we throw a runtime exception, and otherwise, we use the correct result. So the function signature of this function is given two doubles, produce a double. The behavior of this function is given two doubles, I either produce a double or I kill your current thread, which is quite extreme behavior in my opinion, that my function decides to do that. And the worst part is, the only way to know that this is the actual behavior of the function is because I took the time and effort to write a bit of Java doc on top of my function. And of course, you're all smart people and such. You always write Java doc like this on all your functions. And of course, you always read the Java doc before you actually call a function. So you will never get this in production. But sometimes you might have a team member which forgets either one of the two. And then you kind of have to hope you have a unit test that catches this, or else you're going to have a bad day. Another way to solve this in Kotlin is using its nullability system. So here we see the function signature now is given two doubles, produce a double, question mark. In Kotlin, nullability is part of the type system. You have to say if a value is either nullable or not nullable. And if it says a question mark, this is now a nullable variable. So now we can just do check if b is 0, return null, or else the correct answer. By the way, this is a good idea in Kotlin, not in Java. Let me make that clear. Because Kotlin won't allow you to actually perform operations on a nullable value without actually checking it or using the special question mark dot operation, which basically says if the previous value is non-null, then execute this function, otherwise do nothing. And this actually creates quite a nice way of programming. Since we can now just call our divide, question mark dot, if the previous result went correctly, now do it times 2. We continue. If the previous went correctly, now we can do a divide again. And in the end, if anything went wrong, we have the else operator now, which is called like that because the question mark is the hair if you turn it halfway up. If the previous value is null, return 0.0 instead. So now we can basically just think in the happy flow. In all these functions, I don't have to consider if anything happened, if anything went wrong. So that's a very powerful way that Kotlin's nullability system adds. The problem here, however, is that while this doesn't show up in the type signature, if something goes wrong, at least I know why it went wrong. Because I get this nice error message that I cannot divide by 0. However, with Kotlin's nullability system, I just get null. So I miss an error context. So now the problem is, in runtime exceptions, I have an error context. I exactly know what's wrong, but I don't know it can happen. And with the nullability system, I know something can happen. I have an error as return type, but I don't have a context. And I kind of want to have my cake and eat it too. I want to have both an error context and error as a return type. And in order to find the answer for that, that's where I discovered the error library, which is a library for Kotlin. It's still relatively new. Its 1.0 release was September last year. They are very, very busy still developing it. It includes some monads. It includes some improvements to coroutines. It has optics and some metaprogramming. And we'll go into monads, optics, and metaprogramming today. And I just want to say amazing support, because at some point I found a bug, and even before I could submit the issue, one of the developers already like, okay, got an issue, and 2 hours later it was just fixed. So they are amazing in support. So let's talk about monads, and specifically the item monad. So there's this paradox in the monad world that once you truly understand what a monad is, you can no longer explain it. So good thing for you, I'm still trying to learn what a monad is, so that means that I can explain it to you. And for all practical purposes, a monad is just a wrapper around a return type. And this is because either a function wants to return something now, but either can't or can't yet. For example, in JavaScript, like the future is a monad. The function wants to return something now, but it doesn't have the value yet. So it just basically returns a wrapper around that value that can deal with the fact that it's not there yet. So monads, in essence, are just wrappers around return values. So what's the item monad? It's something called what we call an error monad, which means it has an error channel. In this case, the IDER has 2 generic types. There's a left type and a right type, where on the left generic type is an error context, and on the right generic type is the value we're actually interested in. To kind of remember which is which, it's just right is right. And if you're thinking now, that's quite weird terminology, a lot of people would agree with you, but this is basically the industry standard, so we just have to live with it. Another important thing is how the IDER is implemented. And it's implemented as a sealed class, which means that we defined a left and a right implementation of that class. And because it's sealed, these are the only 2 possible implementations of this type. And that has some advantages we'll see a bit later. And as you can see, you can't create an instance of an IDER. You can only create an instance of a left or a right. So an IDER is either an instance of left or an instance of right, but never both. So how do we go on creating an IDER? Well, we're going to change a function signature to given 2 doubles. I either return an instance of left containing a string with the error message, or we return an instance of right containing the correct value. And we can just, if b is 0, create a new instance of either.left. In Kotlin, we don't have to use a new keyword, so this is basically just creating a new object. Or else we return an instance of right containing the correct answer. Kotlin also has something called extension functions, which add functions to existing objects. So if you want to be more lazy, we can just write this, and this does exactly the same. If you want to be even more lazy, we can just do either.catch. And what this does is it will basically place a try-catch around it. If it throws something, it will return an either.left containing that throwable, otherwise an either.right containing the correct value. You can also see that our function signature has now changed that to represent that. You also see the asterisk back. That's because Kotlin's result type basically does this. It's basically an either with on the left side a throwable and on the right side your correct value. And if that's all you need, I would just suggest using Kotlin's result type. If you, however, want something else as a left side, then eithers are actually quite good for that. We can also, if we want, change the throwable to, for example, a string by calling functions like map_left. In that case, if it's an instance of left, it would change it, otherwise nothing will happen. If we can map the left type, we can of course also map the right type. If it's and now we have a map function with which, if in case it's an instance of right, this function will get called, otherwise nothing will happen. So now we know how to create an either, but either, like I said, it's just a wrapper around the value. We actually need to get the value out of it. So how do we do that? First, we create our either. And then, basically, to get the value out of it, we need to deal with the fact that it might also be wrong, that something went wrong. Now, one thing we could do is just call our null, which says it's an instance of either.right, give me the value, or else just give me null. You can also see that double now is a question mark there. We could do things like get or else, which means if it's an instance of write, give me the value, otherwise give me 0.0. But the thing with this is, if you're using it like this, we're kind of ignoring the error context. So we kind of might as well just use Kotlin's nullability system in the first place. So we want to do something with the left result. And this is where we can pattern match over it. So we can pattern match over my either. And the when is basically Kotlin's switch statement in Java. And the is sign is an instance of check. And well, these days Java has a better instance of check. But Kotlin actually is a very, very cool trick that if it checks if it's an instance of either.left, it automatically casts my either to an instance of either.left. So if we call my either.value there, it will actually be a string. Same goes for, we can check if it's an instance of either.right, and now my either.value in there is actually of type double. So we can do things like times 2 on it. And in the end, we have a get or handle, which basically, given if it's a left, we try to recover it and turn it into a right. Now, in this particular case, we can't really turn a string into a double, so we can just log the error and return the default value. And basically, the way you work with monads is very similar to the way we did things with the nullability system in Kotlin. It's so similar, I can just put them under each other. Where you first call our divide function. Then, if the operation went correctly, we can execute the next function. So we use map. If things went correctly, we can execute the next function. You see here there's flat map. Flat map and map are exactly the same. The only difference is if your function returns an either, use flat map, otherwise use map. There's all mathematical explanation why this is a good thing, but in practice, that's basically all you need to know. And in the end, if something went wrong, if either something in that whole thing returned a left, or in the bottoming returned a null, then we give you a default value instead. So we can basically continue our business logic in the happy flow, and only in the very end we have to think about, what if something went wrong? Oh, let's do this instead. So now we know how to create an either and how to deal with it. Let's see how it would affect the real-world application. And for this, I made a bit of a pseudo Spring Booty application because I figured that would probably be the application most people would be familiar with. We'll first make it without eithers, and then we'll see what eithers can do to improve it. So we create an application we're at a conference, so we can book speakers for a conference. So we have 3 repositories. We have something to get a speaker, something to get a conference, and a booking, which stores a booking, which is just a speaker and a conference. And that returns a booking ID. So our service would probably look something like this. We get a speaker, we get a conference, we create a booking, and we store the booking. And the controller just calls the service, gets a booking ID back, and returns HTTP 200. And this will probably work, but it's a very naive implementation. Because what about errors? What if, for example, a booking couldn't be found, or a speaker couldn't be found, or a conference couldn't be found? So we can fix that. We can just add a try-catch, make sure our repositories throw nice domain exceptions as such. And in case it throws a not found exception, we return a 404, and otherwise we can just return a 500. And this will work. It's not my favorite solution. We'll see what eithers can do to help. So let's introduce eithers. And we'll start by creating the left side of the either. And I really like to use a sealed class for this as well. And we'll see why in a second. So we create a sealed class bad state, and we basically add our domain errors to it. So we have a not found domain error, and basically a catch-all. If an exception happens, that will be our domain error. So this will be our left side of the either. So we'll refactor our repositories, So now they all return an either, which is either an instance of left with a bad state or an instance of right containing the correct value. I'm going to skip the service for a second and move straight to the controller, where, again, a lot of code. We'll go through it one by one. So we call a service where we get back an either that's either an instance of left containing a bad state or an instance of right containing a long. Then we are now forced to pattern match over it. We have a wrapper, not a value, so we can't just return HTTP 200. We're now forced to make a conscious decision about, hey, what should happen if anything went wrong? Well, if nothing went wrong, now it's easy. We can just return the HTTP 200. And if it's instance of left, oh, we're now faced again with a sealed class, which we can pattern match over. And if it's instance of bad state, not found, we can just return a 404. And otherwise, we can just throw the exception, or log the exception and give back an internal server error. And on the surface, this looks very similar to the try-catch. But the big difference here is that I'm now forced, basically, to write this try-catch, because I cannot get the value out of my either without dealing with an exception, without dealing the error state. And by using a sealed class after left, I'm now forced to pattern match over all possible implementations. Because Kotlin's when, the switch statement, is something that we call exhaustive, which means that it needs to have all the possible branches, because the compiler knows there are now only two possible implementations. If I would add a third implementation later down the line, it would know this when statement is not complete. So if I would add a duplicate booking exception at a later point in time, this will now throw a compilation error. Hey, there's a domain exception that you didn't write code for yet. So for small applications, this might not be a big thing, but in a bigger application where you have multiple teams maybe working on the same thing, adding domain exceptions and such, this is actually a very powerful tool to get compilation errors instead of having to remember all the places where you call that function. Lastly, now we have the service left, and this is a bit I don't really like about the either, is that in order to create a booking, we need a speaker and a conference. But these two contain our eithers, so eithers are wrappers, we need actual values. So we need to do some flat map magic in order to get the values out of it, to create a booking and store it. And this can basically make your code quite ugly quite quickly. It's one of the downsides of the monadic way of working. And this is where, and I kind of want to have that readable code and the compiler checked and error handling. So I kind of want to have my cake and eat it too. And this is where arrows, in my opinion, one of my favorite feature from Arrow comes in, something called monad comprehension. And that's basically a way to make working with monads easy. All we have to do is create an either block like this. And now, if we within that block create an either, it now has a .bind method at the end, which basically says, if it's an instance of right, get the value out of it and put it in the right value. If it's an instance of left, just short circuit the function and return that left. Which means that on this line, we can only reach this line if the previous statement went correctly. And we can, in the end, return the value. We also now see that our function is suspended. This is Kotlin's coroutines. This is because Kotlin's Arrow team uses the coroutine framework in order to do this short circuiting. If you don't want your function to be suspended, we can just use either.eager, and we fix that. So how would this look like in our service? We now have an either.eager block. We get our speaker, and we call .bind on it. If that went correctly, or if that didn't went correctly, this function would instantly return back with our instance of either.left. If it went correctly, we go to the next line. We can get a conference, call .bind. Now we can just create a booking, and we can store the booking. And as you can see, this is basically the same code we had before. So thanks to the either comprehension, we basically don't have to deal with the downside of monads. We can just do our normal programming, but still get all the compile time safety that eiders offer us. So what did we learn? We learned that we can get compile time safety from eiders, and we can basically still do imperative programming by using the eider comprehension. And that's why it's my favorite feature from Arrow. So that was basically the stuff that you can use tomorrow. Arrow also has some really cool stuff that's maybe not always as useful to you, but since it's quite cool, I wanted to demo it anyway. First of it is optics. And optics are there to support the immutability pattern. I can assume you all think immutability is a really good idea. Otherwise, I have a different talk that goes into that. So immutability is good. And Kotlin's data class is a very good way to support it. It's quite similar to the Java's record class, but it also has a copy method that I'll show in a second. So let's create some data classes. We have a person that has a name and a city has a name and a street just has a name. So we have this nice deeply nested immutable data structure here. What if you want to change the person's name? And that's actually quite easy in Kotlin, because Kotlin has this copy method where we can just say that give me an exact copy of person and just change the name, which is why immutability is a lot easier to do in Kotlin than in Java. But the thing is, what if I want to change the street's name? Now we have to call person.copy, set the city property. Now we have to call person.city.copy, set the street property. And we have to set person.city.street.copy. And now we can finally set the new street name. That's quite a hassle. And I still want to use the immutability pattern. So I kind of want to have my immutability, and I want to have ease of state transitions. So I kind of want to have my cake and eat it too. And this is where lenses come in. And a lens is an object that looks at a specific property of another object. So if we could, for example, create a lens for the city property of person, where we'd have to define a getter and a setter. So this lens zooms in, given a person on one single property, and using that lens, we can either get the property from that person or modify that property from a person. Again, right now, this is not very useful. We could have just used a copy method for this. The power comes if we create more lenses. So we can now create a lens that goes from the city to its street property. And a lens that given a street goes to the street name property. And now we can combine those lenses. So we now have a lens from person to city, from city to street, and from street to street name. And by composing those, we can go all the way from person to the street name. And now we can use this lens to instantly change the street name in a single decoration, which is quite cool. But I can hear you think, yeah, that's really cool, but writing all those lenses is basically more work than doing the copy thing in the first place. Well, Arrow team thought the same, and they're here to help, because they can just generate these lenses for you. All you have to do is write an add object for the data class, and in the end define a companion object. The companion object in Kotlin is basically the place where static functions and static variables are put in. And what Arrow will do is for every parameter or constructor parameter, it will put a lens for that parameter in the companion object. So if you want to do exactly the same thing, after it generates, we can just call person.city.street.name.modify, and we can just set a new street name. And we don't have to do any lenses creation ourselves. So quite a cool feature in my opinion. Aside from that, optics also have things like traversals that help you deal with iterables if you want to do operations on every element, for example, in a collection that's deeply nested. There's some prisms which allow you to help with sealed classes. and ISOs, which help you deconstruct and reconstruct objects, as in get an object, turn it into like a tuple of values, and given a tuple, return it back into object. And you can all compose those to do whatever you want. So you can do easy operations on very deeply nested data structures. So what did we learn from that? Lenses allow us to see and modify a single attribute. We can compose those lenses to create very powerful lenses, and Arrow just generates these things for you. And I want to end up talking about smart types, which is something I got quite excited about. And for that, to see what that is, we first need to take a bit of a look back to our how we solved our divide function. Because we first tried to solve it using a runtime exception, then we tried to solve it using Kotlin's Nullability System, and in the end we solved it using an either. But there's actually a fourth way to solve this problem, and that's actually surprisingly easy. We just add a precondition that b must be positive. And now we basically said you're not allowed to call our function with b that is at least 0. So we are forcing people to do an if check. That's basically it. Just say people should do a certain thing, and now magically we don't have to take that into account anymore. Of course, this has the same problem as previously, that nobody bothers to read Javadoc. So we could enhance this by, for example, creating a data class positive, which contains a double value. And basically in the constructor, we just check that that value is greater than 0. And now we can just make b a positive. And now it's suddenly impossible to call the divide function with a 0. Did anyone see the problem here yet? There are actually two problems. We now have some object overhead, since we have to wrapper around our double. So we're basically creating twice the objects. And we're actually back to a runtime exception, because that require throws a runtime exception in case it's not correct. Although the exception happens sooner, so that's good. Now let's see if we can solve these two problems. Well, the first one is actually quite easy. Kotlin also supports something called a value class. I think Java is also working on this, where during compilation time, this is a class, but at runtime, it actually removes the class overhead and it's a double. So at compile time, you have all the advantages of a class, and at runtime, it's just a double. So we save this object overhead. And for a runtime exception, basically all we need to do is add the error analysis Gradle plugin, which is a plugin that hooks into the compilation step of your program. And if we now try to create a positive with -1, we suddenly get an exception that says, hey, I see you try to create a positive with a value -1, and the value should be greater than 0. I will not allow you to compile the code. Which is, when I saw this, absolutely awesome. So what is the error analysis plugin? Basically, it allows you to add pre- and post conditions to things like numbers and strings. And it has a bit of like the Kotlin's nullability checking thing, where you kind of need to prove to the compiler that the preconditions have been met, or else it will not allow you to compile your code. It also has some laws which add things to third-party libraries, and unfortunately it currently only supports Gradle. So let's take a look at these pre- and post conditions. I say pre- and post conditions, and we see require here. That's because this library has been a bit older, and Kotlin at some point introduced the require keyword when they already had the pre-keywords, so now Arrow just supports them both. And since require is the Kotlin natives, I would suggest using that. So we do require that x must be greater than 0, and afterwards, in post, we can specify that the value that we return is now greater than 1. And we know this for sure because what comes in must be at least 1. And what comes out, we do a +1, therefore must be at least greater than 1. So once we add those pre- and post conditions, a few things happen. If we now try to call the function with a 0, that doesn't meet the precondition, Error analysis plugin will see this and won't allow you to compile your code. If we call it with the value, the parameter of bar, arrow of the plugin doesn't know that the value is greater than 0. We haven't proven to the compiler yet that this is the case. So it will not compile. So what we need to do is actually by, for example, with an if statement, prove to the compiler that this value abides to the precondition, and only then the plugin will allow us to compile our code. Out of it comes a new value, my positive int, and if we use call foo with that, it will still compile. And that is because we added that post condition. And therefore, we added information to the compiler that whatever comes out of it is greater than 1. And because greater than 1 also means greater than 0, the compiler knows that, oh, it's safe to call foo with that value. If you now think all those pre and post conditions are a bit much, an alternative way to do it is indeed, again, use our value class with the require, which is a precondition that our analysis will see, and just have an input as a positive and an output as a positive. And basically, this achieves the exact same thing. And I like this approach a lot more than adding pre and post conditions to all my code. It doesn't only work for numbers, it also works for strings. Although, unfortunately, right now only to the string.length. It doesn't work on contains yet. They're still working on that. Where we, for example, require that the string length must be a maximum of 10. Which is, for example, quite useful if you have certain database fields with maximum length. And exactly the same thing happens. If your string is too large, it won't compile. If you just put in a random value, in that sense, it does not compile. And only if you've proven to the compiler that it abides to the precondition, then our code compiles. It also works on lists. If we get a list and we try to get the first element out of it, error analysis will see, like, hey, you haven't checked if the list actually contains the first element. So I won't allow you to compile that. This, by the way, also works on just getting things by index. You first need to prove to the compiler that the array is actually big enough to get that certain element out of it. And otherwise, your code will not compile. And this is a bit stranger from how does this work, since previously we created these classes ourselves. And this is the Kotlin standard list. And that's because error analysis added laws. And this allows them to add these pre and post conditions to existing code. And the team worked quite hard to add these things to Kotlin's collections. And this, for example, a way where they add the precondition to the first method of a list. So when I first saw this, I thought, this is absolutely amazing. I'm going to use this everywhere. Because like I said, things like database field constraints, which I can now just make sure that my code won't compile if people don't abide to them. Or my external services have certain constraints. Basically, this is a great way to make illegal states non-representable. You can't create an instance of an object if you didn't do the correct checks, because my code just won't compile. But then I did some toying around, and I must unfortunately say, well, it has a lot of potential. At least at this moment, it also has some problems. The first one is it's still somewhat limited. It's only on on numbers, on strings, and on the collections. And with strings, it's only the length and not yet the contains. It's very strict. In one way, you want it to be very strict. On the other way, once you add this plugin, you need to do these checks everywhere. Even if you, for example, get data out of a database and try to turn it into a domain object, yeah, you need to check if all those values are still correct, even if it's a trusted source. You can opt out of it, like don't check this bit, but then you have to add error analysis specific code to that, and I don't really like that. It also doesn't really work with deserialization or reflection, because that ignores the constructor. So the analysis plugin cannot check this. So if you're using Jackson or Hibernate, unless you're writing custom mappers this won't find it. So that basically means this only works in your domain code. And it doesn't really support the streaming API that well. Because if we, for example, create a list and we then do a filter that all elements are positive and then try to map it to a positive, the checking and the mapping happen in different scopes. And the compiler cannot get the information from the first scope and use it in the second scope. So the only solution to that is do the checking and the mapping in the same scope with, for example, map not null. Which is also a bit of a shame because that would mean I would have to change my way of working to use this plugin. But the prospect of it is quite awesome. I see a lot of potential in it, and the team is really working hard on this to make to add these features. And it's a great way to move the runtime errors to compilation time, and therefore we can make illegal states non-representable. And because I needed the cake analogy, I would say this is the cherry on top. So concluding, we can have both an error context and error as a return type, thanks to IDERs. You can have both all this compiler support and readable code, thanks to the monad comprehension. We can have immutability and ease of change, thanks to optics. And we can move our runtime exceptions to compilation time exceptions, thanks to the error analysis plugin. So I think we can safely say that thanks to Arrow, we can have our cake and eat it too. That was it for me. Thank you so much for listening. If you have any questions, feel free to ask them now. Add me on any of these ways. If you want to see the slides, there's a link over there. Or I'll be walking around today and tomorrow. Just ask me. Like I said, I wasn't lying about being very passionate about this thing. I love to talk about it. So thank you very much for showing up at this time. And have a great conference. Nah.